This is the first video on section 5.4, local extrema. So you've heard this expression before in Calculus 1, remember? And what would you do to look for local extremes in Calc 1? You would take the derivative, find the critical numbers, and then use the critical numbers to find the local maxes and the local mins. We're going to do something very similar in Calc 3. So recall from Calc 1, you have local maxes and local mins. These aren't necessarily absolute maxes or absolute mins. So this point C right here is a place where this function has a local max. This is our local max right here. It is not an absolute max. This function doesn't have an absolute max, and it does not have an absolute min. But right here at C is what we call a local max. And remember the definition. We can find an interval around C where f of c is greater than or equal to f of x for all the x's in this interval. Now for a function of two variables, we have something similar. We're going to talk about what it means to have a local max or a local min at the point AB. Now in the real line, we take an open interval around a number. In R2, we take an open disk around a point AB. So what we do is we just take the circle of radius r around AB, not including the boundary. That is what that was in this definition. These definitions 145 and 146, that's what we're saying here when we talk about the distance between xy and AB being less than r. So now, what does it mean to have a local max there? It means that f of xy is less than or equal to f of AB for all xy in this circle. A local min means that f of AB is less than or equal to f of xy for all xy in that circle. These are our two definitions. Now, remember in Calculus 1, we had something called a critical number. That was a place where the function existed, but the derivative was either 0 or did not exist. Okay? Here, definition 147 is of a critical point. That is a place where the function exists, but either both first-order partial derivatives are 0 or one of them does not exist. That's what a critical point is in R2. Remember from calculus. Why were we interested in critical numbers? If a function had a local max or a local min, then that point was a critical number. And so what we did is we found the critical numbers and we looked for the local maxes and local mins at the critical numbers. We didn't always find them there, but that's where we looked. Same thing for theorem 148. It says if your function has a local max or a local min, then that point is a critical point. If it has a local max or a local min at AB, AB is a critical point. That's not saying that just because a point's a critical point, it has a local max or a local min there. What it says is that's where we look. We find the critical points and we look there for local mins and local maxes. Definition 149 of a saddle point. Saddle point is a point that is a critical point, but the function does not have a local max or a local min there. And finally, theorem 150, the second partials test. We'll use the second order partial derivatives to look for local mins and local maxes. And so we're assuming we have a critical point of the form where f sub x of AB and f sub y AB are both 0. Those aren't the only kind of critical points that we have, but they're the ones that we're going to test with the second partials test. Then, at AB, we calculate this number here. We have the second partial f sub xx times the second partial f sub yy of AB minus we have f sub xy AB squared, which in the context of the theorem, I didn't state the whole theorem, but by the hypothesis of the theorem, f sub xy and f sub yx will be the same for this particular type of function. That's not always true. but it will be true in this case. So I did not write the whole second partials test here. Now, we calculate this number. We check to see if this number is positive or negative. If it's positive, and this second order partial is negative, we have a local max at AB. If DAB is positive, and f sub xx is positive, we have a local min at AB. If DAB is negative, we have a saddle point at AB. Remember, we have the word test here. This is the second partials test. Remember, one of the things that you learned in Calculus 2, you had a lot of theorems with the word test in them. A test can be inconclusive. So what happens if DAB is actually equal to 0? Then the second partials test doesn't give us any information. So when you have something called a test, that means you perform this test, and if you get certain results, you can make certain conclusions. If you don't get these results, then you can't make the conclusions, because the test will be inconclusive then.